Give it just another 30 seconds or so, see if anyone else decides to show up for today. Okay, we'll get started today. I think today is going to be a light lecture because chapter 6 we'll be able to work on. We have this week and next week. And I also am going to Miami tomorrow morning with 12 girls. Well, I don't want to say they're girls. They're worse than girls. They're 40-year-old women, and they all have a mission to prove they are not 40. So I got to rest up. So because of that, we will probably be done around 7 today. Crazy. It's going to be crazy. You don't have any labs this week. Nothing due. Okay. And you don't have any homework this week. So it's just going to be a light week. Thanks for getting the test done. I graded there was like one question where you had to explain how soap worked. I graded that. So that should have been calculated now within your grade. So you should be able to see what you got on the exam through Moodle. So we kind of went away from math for a while there. And now we're going back to it. So all that dimensional analysis stuff, we're going to bring it back. We're going to start doing that. We're going to use conversion factors again. We're going to use them for some different concepts. And I think chapter 6 is like the chapter that keeps on giving. There's a lot to it. So that's why I scheduled out 2 weeks for us to have this. The chemical compositions. How much sodium? All right, so sodium is this metal that is actually really important. It's a dietary mineral that we need to consume in order to regulate a lot of hold on one second. To regulate blood pressure and things like that. We don't want too much of it. Otherwise, we will have high blood pressure, but we do need to consume salt in some way. Or we need to consume sodium in some way. And so the way that we receive our sodium is through eating sodium chloride, which is table salt. The FDA says that we need like 2.4 grams of sodium per day. That doesn't mean we need 2.4 grams of sodium chloride a day, though. We actually can have more than 2.4 grams of sodium chloride because the sodium chloride will contain sodium and chlorine. It's just specifically saying sodium has to stay at 2.4 grams or less. So is there a way for us to calculate how much salt we get to eat if we know how much sodium we need? And there is, and I will show you guys how to do that. It has a lot to do with the chemical formula. So, we have NaCl and we know we get 1 sodium. Why it keeps doing that? 1 sodium for every 1 chlorine ion. The sodium and chlorine ion have different masses though. So we're going to need to look at the chemical formula to see the molar relationship between them. So the information in a chemical formula tells us something about like how much of each thing we have. So when I see, like a chlorofluorocarbon or freon or something like that, it tells me how many chlorines, how many fluorines, and how many carbons I have. This example over here is sort of relating to the sodium and sodium chloride thing, how much iron is in a given amount of iron ore. So transferring or converting between the part and the whole. So before we do that, we need to step back a little bit and talk about counting by weighing. And this shouldn't be really a new concept. They do this in hardware stores. When you buy a set of nails, the person doesn't count all the nails you need. They have some sort of conversion factor, right? And they know that like, hey, every pound is like, 40 nails or something like that. Or every pound is, 3 dozen nails. And so they'll just weigh the nails and get, a rough estimate. The same thing is true for atoms. There are just like way too many atoms for you to count, okay? I mean, the person at the hardware store doesn't want to count the nails because it's a pain in the butt, but they could. You don't have enough hours in your life and in your children's life and your children's life to count the number of carbon atoms in this little dish right here. There's just too many. So we've got to weigh it. So we can look at this problem here. It says a customer buys 2.6 pounds of medium-sized nails. We're going back to those flow charts and the conversion factors. And a dozen of these nails weighs roughly 0.150 pounds. How many nails did the customer buy? So there's two different conversion factors here. One conversion factor is unique to the problem, and that is that a dozen nails weighs 0.150 pounds. Okay, so I know 1 dozen nails is equivalent to 0.150 pounds. There's another conversion factor in here that isn't quite as, it isn't customized to this problem. And that is the conversion between a dozen and individual nails. Because this doesn't say how many dozens do I have, but it specifically says how many nails do I have. So what do we know about a dozen? 1 dozen of anything is equivalent to 12 of them, right? So in this case, 1 dozen nails is equivalent to 12 nails. That is the definition of a dozen. So the first thing here is unique to the problem. Let's say instead of using medium-sized nails, we used large nails, right? That would have a different value. This second value is consistent across the board. Doesn't matter what the nails are, a dozen of the nails is going to be 12 of them. So in this problem, we have a 2-step conversion. We need to go from the mass into this sort of common unit known as a dozen, which is 12. And then from a dozen, we're going to go into the individual number of nails, because this doesn't have a direct relationship between the pounds and the nails themselves. It has to go pounds to dozen and then dozen into individual nails. So conversion factor 1 is going to get us through step 1, which is this here. And then the second conversion factor, this guy here, will move us through that second step. This second one probably feels like a no-brainer. You're like, well, obviously, if I want to go from dozens to individual nails, I would just multiply by 12. But I want you to be setting it up in dimensional analysis. So we take our individual or our initial amount. We had 2.6 pounds of these nails. I know that for every 0.15 pound of the nails, I get a dozen nails. So putting the pounds on the bottom allows me to cancel units. It's the same thing we did in the beginning with like inches and feet and all that stuff. That pound relationship goes to dozens of nails. And then we're going to use that second conversion factor that says, hey, for every 1 dozen nails, we get 12 nails. Again, this one is customized, unique to the problem. This one is just a definition conversion. We know that nails are a dozen is always going to be 12. So when we go through this, and the dozens will cancel, we'll be left with units of individual nails, which is what we wanted. And it says, hey, it's 208 nails. We're pretty much going to be doing the same thing, except instead of pounds, we'll probably have something like a gram. Instead of dozen, we'll have something called a mole. And instead of number of nails, it's going to be number of atoms or molecules. And I'll get us a flow chart with those specific ones a little bit later. Okay, so all right, so there's our 2 conversion factors. Okay, so how does that relate to chemistry? Because nails don't really have anything to do with the chemistry we've been talking about thus far. With atoms, we need to use their masses, and we need to use some sort of definition for a clumping of atoms in order to count them. Atoms are just too small and too numerous for you to count them individually. If you counted for 24 hours a day for as long as you lived, you'd barely begin to even count the number of atoms that are in a grain of sand. Just not going to happen. So is a dozen going to cut it when we're counting atoms? No, because it's only one exponent, right? It's taking a value that was like 120 nals and it's dropping it down to 10 dozen nals. That's not really cutting a lot of the decimal place. It's really only cutting like one decimal place. So we need something that's kind of stronger than a dozen. And that's known as the chemist dozen, which is also called, and you'll hear me commonly call it, the mole, M-O-L-E, or abbreviated M-O-L. So what is a mole? 1 mole is equal to 6.022 times 10 to the 23rd. Whoa, that is a lot bigger than a dozen, right? A dozen would be, 1 dozen, we said, is equivalent to 12. That's like really puny. We can't use that. We need something that's a bigger, got a bigger factor to it. So this definition applies to anything. 1 mole of carbon is equal to 6.022 times 10 to the 23rd carbon atoms. 1 mole of people is equivalent to 6.022 times 10 to the 23rd people. There's probably not been that many people that have existed in all of like humankind, because it's a very, very large number. Don't write it out. Use the exponent button on your calculator. Sometimes this number is also called Avogadro's number. Okay, not avocado's number, Avogadro's number. There's a dude named Avogadro who came up with this relationship. And again, we can see how this sort of applies to everyday objects. 1 mole of marbles is equivalent to 6.022 times 10 to the 23rd marbles. 1 mole of sand grains is equivalent to 6.022 times 10 to the 23rd sand grains. Would we ever use this mole value in everyday counting? No, we don't have enough of anything really in our, I don't know, maybe like blades of grass or grains of sand might at some point, grains of sand or like blades of grass that have existed for all eternity. Maybe we'd start to get close to that, but it's a big number. So we kind of just use it in chemistry when we're counting atoms. And if you're like thinking, wow, man, 1 mole is 6.022 times the 10 to the 23rd. That's like a lot, isn't it? It's actually not as much as you think. 1 mole of copper, and let's, just to beat a dead horse, 1 mole of copper is equivalent to 6.022 times 10 to the 23rd copper atoms, right? Is roughly 22 pennies. Okay, so a mole it's a lot of atoms, but on a macro scale, it's not that much. 1 mole of helium over here, which again is equivalent to 6.022 times 10 to the 23rd atoms of specifically helium, is about 2 balloons of helium. So when you hear us throwing around, hey, I've got, 1.4 moles of silver. This isn't some like astronomically large or small amount. It's something that you could probably hold in your hand. Now, just because they're equal to the same number of atoms does not mean that they're the same thing, right? This is copper atoms. This is helium atoms. So they're going to have different properties and they're going to have different masses. This is going to be much lighter than this, right? 22 pennies is probably going to be heavier than the amount of helium we have in these balloons. So, sometimes people will just write units like, oh, I just have a mole, and they don't give it any specific definition. You got to say, hey, this is a mole of water. This is a mole of copper, because a mole of water and a mole of copper are going to be totally different from each other. Just like you wouldn't say, oh, I have a dozen. Like someone comes in and they're like, oh, I have a dozen. Debbie, I'm working. Thank you. You're like telling your friend, you're like, yeah, I got a dozen. You want to come over? I've got a dozen. And they're like, a dozen what? And, they don't know if you've got a dozen cakes or a dozen movies to watch or like a dozen pickled eggs. Who knows what you have. So make sure you're giving me the specific compound or element that you're working with. So using Avogadro's number, Josie, what are you doing? What are you doing? Here's my boxer. She's coming to say hi. Can you say hi? Everybody needs to leave me alone. Go, go. Lock the door. So anytime you have two things that equal each other, it's a conversion factor. Yay, we can do dimensional analysis. So we can go from one unit to another because we have two separate things here. And I know there's not really a unit on this end because it kind of changes. You can think of it as like parts. Okay, so 1 mole is equivalent to 6.022 times 10 to the 23rd parts or individual units of it. If it's marbles, it's marbles. If it's an element, it's atoms. If it's a compound, it's molecules. So let's look at a problem here. Oh, and if you're wondering why is it 6.022 times 10 to the 23rd and not something else? It's the numerical value of the mole is defined around carbon. We use carbon a lot as our central unit on the periodic chart. So if I had 12 grams of pure carbon 12, the isotope carbon 12, and I had exactly 12 grams of it, that is how many atoms would be in it. So that's why we use that. Okay, so let's say we're given that you have 3.5 moles of helium. And for whatever crazy reason, you want to know how many helium atoms that is. All right. So what is the relationship between moles of helium and helium atoms? Well, this is our Avogadro number relationship. 1 mole of anything is equivalent to 6.022 times 10 to the 23rd individual parts, or 1 mole of helium is equal to that many helium atoms. So really, it's just a matter of setting it up so your units cancel. We start with our given information, which is the 3.5 moles of helium. And I use this as my conversion factor. So we turn it into a fraction. Now, what I want to put on the bottom is whatever my given unit is. If mole is what I'm starting with, I want to put the 1 mole on the bottom so that it cancels. I'm going to put the large number of atoms up on top, and then I'll be left with just helium atoms. I want you to go ahead and plug this into your calculator, this one and the next one, because I want you to get comfortable with using your exponent button, either that EE button or times 10 to the 23rd. If you're using times 10 to the 23rd, get into the habit of putting it in parentheses. You really only need to do it. I would just do it all the time, but definitely when it's under the fraction bar. So 3.5 times this 6.022 times 10 to the 23rd, you should get 2.1 times 10 to the 24th. So if you're not getting that on your calculator, something has gone awry, some exponent has been put in incorrectly, or you've doubled up on exponents. We just want to make sure that we can get that. I'm going to say something else about this, but I forgot. It'll come to me at some point. Okay, any questions on calculate like the calculator? So Grayson, you got 2.1 E24. Yeah, the E24 is representing this here. That's the E. Okay, so anytime you see, like, if you have a heftier scientific calculator, it's not going to write times 10 to the 24th. It'll go 2.1 with a bunch of decimals, E to the 24th. So always look at the very end of the number. Don't forget that. I remember what I was going to say. So if I'm asking you to calculate helium atoms, you better end up with a pretty big freaking number. Okay. If you end up with like 3, something has happened. We don't want to have 3 helium atoms. We're going to have a lot of them. So you may have multiplied or divided in a weird way. What if we want to go the other direction? Okay. So let's say instead of giving you moles, I gave you atoms. So like this one here, we have 1.1 times 10 to the 22nd silver atoms. And I want to know how many moles that is. Well, the relationship is the same. This is sort of that 1 dozen equals 12. It doesn't change. So the relationship between atom and mole, even though it's something different, silver, it's still the same thing. 1 mole of silver is equivalent to 6.022 times 10 to the 23rd, in this case, silver atoms. The difference comes in how we set up the fraction. So if you look here, okay, the atom is what we're starting with. So the atom needs to go underneath the fraction bar. The mole will go on top. That way the atoms cancel. Now this, you have to put in parentheses like this, or you need to type it into your calculator as 6.022 EE, the EE button, 23rd. Okay, I like the EE button because it kind of preserves all the information. It like clumps it together for me. When I write it like this, you don't have to use parentheses. If you're typing it in this fashion, you have to use the parentheses, or what your calculator is dumb. So it's going to do whatever you tell it to do. So if you don't use parentheses here, it's going to take this number, it's going to divide by the first part, and then it's going to multiply the whole number by the second. You're going to get a really, really big number. So we want to make sure that it's dividing by both of those units. So go ahead and give it a try. 1.1 times 10 to the 22nd, and we're going to divide it by Avogadro's number this time. And if you want to, if you know how to like preserve numbers in your calculator, like save numbers in your calculator, you might want to save Avogadro's number in there because we use it quite often. So that 1.1 times 10 to the 22nd divided by 6.022 times 10 to the 23rd. Don't get freaked out by this. This is just scientific notation for 0.018 moles of silver. So again, if you're having weirdness with your calculator, let me know, because I don't want you to miss points because of a calculation error, like not even a calculator error. Just plug in and chug in.
Is there a way to do it without, like, can you subtract these, or
can I subtract these two
like
numbers?
the exponent part? Like, is there any way to do it without the calculator?
These two, dividing these two numbers by each other?
Yeah, I mean, like, can you divide like 1.1?
I mean, you could take the 1.1 and divide it by the 6.022 and then subtract the exponents if you wanted to. I'm not going to teach it that way, but I mean, I get what you're saying. You could do it that way.
Okay, I just wanted to make sure that that would be okay, because I don't have one of the nice calculators.
Yeah.
And
do you have an iPhone?
Yeah.
Okay, so if you go to your calculator, you go to your calculator on your iPhone and you turn it to the side. You have the EE button sits there right next to the 1.
Okay.
So you may want to use that. Yeah.
Okay.
I mean,
okay.
I understand what you're saying as far as subtracting the exponents. You could. I'm not going to teach it that way though.
Okay.
Okay.
Yeah, that was just my backup plan, maybe. If
yeah, I get it.
I wanted to make sure. Okay, thanks.
Yeah. So I'm gonna have you guys do one of these, but first I want to start us off on like a flow chart, sort of a master flow chart. So on the top, I'm gonna put, let's say, mass, and then we'll put moles. And then we'll put particles. Okay, underline that, that's sort of the title. Element and compound. Okay, so we have grams of the element here. We have moles of the element here. And then we have number of atoms. Now, under this area, I want you to write almost the same thing, but instead of grams of element, we're going to say grams of compound. Sorry, G of compound. Those are kind of smushed together. Grams, G. Grams of compound. moles of compound. And then instead of number of atoms, we're going to say number of molecules or formula units. So, when I'm talking about having 1 mole of a compound, like 1 mole of water, 1 mole of H2O, that is going to be equivalent to 6.022 times 10 to the 23rd H2O molecules, right? Because what's the most basic unit of water? It's H2O. It's a molecule of H2O. It's not hydrogen. It's not oxygen. It's those combined together in a packet. So let's put some arrows in between here. And we can go in either direction here, right? And what do we use here? This is Avo's number for both of them. So 1 mole of the element is equivalent. You guys already know this. Well, you know of it. 6.022 times 10 to the 23rd atoms. The same thing is true if we're dealing with a compound. 1 mole of a compound, any compound, is equivalent to 6.022 times 10 to the 23rd molecules. We will fill the rest of this chart in over here, and we're going to go up and down as well. So make sure you have space for that. But why don't we just work with water since we've got the water thing laid out here. So how many moles? Moles of water are there from 3.97 times 10 to the 25th water molecules, H2O molecules. And if you want to kind of relate this problem to our master flow chart that we have up here, we're starting with the number of molecules. We're ending with moles of the compound. So we're just doing 1 step here. I'll give you all 2 minutes or so to set it up. Don't get freaked out that it's a molecule. It's the same setup as the atom thing, Avogadro's number. We'll see you guys in like 2 minutes. Okay. So we are given something about the amount of them that we have, or the number of particles. So we're in this left, or rather, sorry, this right-hand portion. And we're dealing with a compound, so we're in this lower right-hand corner. We have 3.97 times 10 to the 25th H2O molecules. I'm trying to find moles of water. Just say, because this number is really clunky and I want something a little more, a little easier to use. So I start with my given information, which is this 3.97 times 10 to the 25th H2O atoms. And I'm going to use this conversion factor, which is our chemist dozen conversion factor. I want to put, not H2O atoms, sorry guys, H2O molecules. Dealing with molecule here. I want to put the molecules on the bottom, the 6.022 times 10 to the 23rd H2O molecules on the bottom for every 1 mole of water. That's going to allow the molecules to cancel and we'll be left with just moles. Now, again, you need to make sure that this is like put in parentheses or you're using that EE so the calculator doesn't do something you don't want it to do. You're entering answer here, 3 significant figures, so 65.9. And the unit on this is moles of H2O. If you ended up with a really, really big number, it's because you didn't put parentheses. I'm just gonna double check myself here. 6.022. Yeah. So I feel like this part isn't that bad. Going between moles and individual particles or vice versa, it's the same conversion factor every time. It's just moles using Avogadro's number. This area here is where it gets a little bit more complicated, going from moles to grams or grams to moles. Just like when we were dealing with the NALs, it's what the weight ratio is to the dozen NALs has to do with what type of NAL is it. Is it an iron NAL? Is it a galvanized NAL? Is it a big NAL? Is it a small NAL? This is also dependent on what the thing is. Is it sulfur? Is it silver? Is it water? Is it ammonia? Those will all have different relationships. So let's look at that. So these 2 pictures have the same number of NALs, but the weights on these are different. So looking at those 2 piles, which one's going to be heavier? Probably the 12 NALs on the left, right? Those are, unless it's a really, really dense metal. Let's say they're both made out of iron, so they have the same density. The ones on the left are going to weigh more because they're bigger. There are 12 on each side, but the left one's bigger. The same thing is true when we're talking about that chemist dozen or moles. On the left, I have a mole of sulfur. On the right, I have a mole of carbon. Both of those 2 dishes contain 6.022 times 10 to the 23rd atoms of their constituent element, but they have a different mass. Sulfur weighs 32.06 grams. Carbon, 1 mole of it weighs 12.01 grams. So where are those numbers coming from? Do they look familiar? They should. They're the atomic masses on your periodic chart. So if you pull out a periodic chart right now, that mass value is not just telling you the number of protons and neutrons, it's also second-handedly working as this thing called a molar mass. Molar mass, the amount of mass in every 1 mole. So you don't have to have these molar masses or that relationship memorized as long as you have a periodic chart. So the atomic mass unit, or the AMU, is defined as 1/12 of the mass of a carbon-12 atom. Again, this whole idea of it being kind of surrounded around carbon. Let's look at copper. So find copper on your periodic chart. And we'll see that copper has an atomic mass of 63.55 AMUs. That is also telling us that one mole of copper atoms has a mass of 63.55 grams. Another way to write it is in molar mass, where we would say, hey, 63.55 grams per every 1 mole. Well, anytime we have a double unit like that, it becomes a conversion factor, right? We can go from grams to moles or moles to grams because we have 2 units. Note that when you're seeing that number per mole, it's like saying 63.55 grams per mole, per 1 mole. Okay, so 1 goes with the mole, the number goes with the gram value. Clear that out. So, the number gets coupled with the gram, and there's an inferred 1 here. Well, that's useful because now I can go from a mass value into a mole value, or vice versa, a mole value into a mass value. Because how often do scales give you things in moles? Never, because it's dependent on the individual material you're weighing. So it gives it to you in grams. Here are some values for a couple elements. We'll notice that they're all talking about 1 mole. 1 mole of sulfur, 1 mole of carbon, 1 mole of lithium. They're the same number of atoms. This is 6.022 times 10 to the 23rd. So is this, and so is this, but they're of different atoms. Sulfur being the heaviest or the largest atom with the most number of protons and neutrons, carbon being the second heaviest, and then lithium being the lightest. So all of these things, 1 mole of each of them, weighs a different amount. Just like 12 large nails is going to weigh something different than 12 small nails. So the lighter the atom, the less mass you're going to have in every 1 mole. So let's say we have some carbon. Okay. We have 0.58 grams of carbon. And I want to know how many moles of carbon that is. Going from a gram value into a mole value is going to require your molar mass. It's not something you have memorized, but it is unique to the problem. So because we're talking about carbon, I don't want to use the molar mass of platinum or hydrogen. I want to use the molar mass of carbon. So the molar mass of carbon tells me that 1 mole of carbon will always weigh 12.01 grams of carbon. This is the molar mass. Mass. And where did it come from? Periodic chart. So we start with our given information, which is grams, 0.58 grams. And we set up the molar mass where we put the gram on the bottom, because again, we want the gram and the gram to cancel, and we put the mole on the top. Remember, this is a molar mass, so it's per mole. Grams go away, and we end up with 4.8 times 10 to the negative 2 moles of carbon. And again, don't get freaked out by this. This is the same thing as 0.048 moles of carbon. So now we can fill in the arrows between the flow chart of gram and mole. Let's do that while we're here. Okay, so filling in here. I'm not going to do this yet. That requires a little bit more work. But we know that in order to go from grams of an element into moles of an element, or vice versa, we need to use the molar mass of the element. And if you want to give yourself an additional note, in parentheses, put periodic chart. You know where you're referencing or where you're trying to get this information for molar mass. Let me give you one in that part of the flow chart. So let's say you're given, you have 13.6 moles of bromine. I want you to find how many grams of bromine that is. Okay. You're given moles. I want you to find grams. On this side, it is unique to the problem. So it is unique to what element you're talking about. I'll give you 2 minutes to set it up and then we'll go over it together. Okay. So this one is similar to that carbon problem, except we're going in the other direction and it's not carbon, it's bromine. But we're still needing to use the molar mass for bromine off the periodic chart. I don't have a periodic chart, so I'm going off of memory. So I think 1 mole of bromine is equivalent to, what is it, 79.9 grams? Okay, cool, 79.9 grams of bromine. So our setup is really, I don't think about it as like, oh, I'm going from moles to grams, so I'm gonna multiply by the molar mass, or I'm gonna divide by, I just set it up in the dimensional analysis and cancel units when necessary. So we start with 13.6 moles of bromine. And all I know is mole of bromine is here, so I need the mole of bromine to be on the bottom. 1 mole of bromine on the bottom for every 79.9 grams of bromine. Students will ask, how many decimals do I have to use? Okay, I'd use, I don't know, 2, 1 or 2. Like you'll see me with oxygen. Oxygen's molar mass is 15.999994, I think. I just use 16 for that one. But look at chlorine's molar mass. Chlorine's molar mass is 35.45, I believe. That one I would not round. Okay, I'm going to use the 35, the point, the 4, and the 5. All right. Anyway, so back to this one. So the moles will cancel. And in this problem, we have to multiply the two values together. So 13.6 times the 79.9. Now, depending on if you used 79.9 or 79.904, how many decimals, your numbers might vary just a little bit. Okay. And that's okay. So don't get freaked out if like your number is like 100th off from mine. You will end up getting the answer correct on an exam. So in this case, 3 significant figures. So I want to keep 3 sig figs. I got 1,086. I need to round that to 3 sig figs. So I'm going to round that to 1,090. And the unit on that is grams of bromine. Is that a yeah? Yes, confirmation, head shake. Miles is like, yeah. Grayson's like, I don't know. Yeah, maybe. Okay. Cool. So we've got this here. You may be even going a step further and thinking, well, if this ties into this and this ties into this, then can I go from this to this? You can, but it's always going to be a 2-step problem. Okay. You can't go directly from grams to atoms or atoms to grams. You've got to go through moles. Sometimes we talk about the moles being like the crossroads in chemistry because you kind of have to go through them in order to do a lot of your unit conversions. So let's do a double step problem. How much does, and I'm going to let you do it on your own. How much does 5.47 times 10 to the 24th sulfur atoms weigh? And when I say weigh, give me grams. Okay. So how much does 5.47 times 10 to the 24th sulfur atoms weigh? I'm not going to tell you where to start and end. Figure out on your flow chart where you're starting, what your given is, where you're trying to end. It is a 2-step problem. I'll give you 3 minutes for the setup. All right. So this problem is a two-step problem. We're given sulfur atoms. So we're starting here on the flow chart, a specific number of atoms. We're trying to figure out the weight or the mass in grams. So I need to get to grams over here. So I have to go through two steps. The first thing I'm going to need to do is take my number of atoms and convert that into moles. Then when I get into moles, I can go ahead and convert it into grams. I cannot go directly from here to here. So don't do that. Follow the flow chart. We're given 5.47 times 10 to the 24th sulfur atoms. We're trying to find the mass of sulfur, grams of sulfur. So first step is Avogadro's number. The most common thing I see people do in these two-step problems is they'll use the molar mass here, and then they'll use Avogadro's number over here. Don't flip-flop those. Make sure you keep them in their respective places. So going from atoms to moles is going to require Avogadro's number. So I'm going to just kind of chain it together here. So I have 5.47 times 10 to the 24th sulfur atoms. If I want moles, which is I'm going out of atoms into moles, I'm going to put the 1 mole of sulfur on top. On the bottom, I'm going to put that 6.022 times 10 to the 23rd sulfur atoms. That's going to take care of my first hop, right? So sulfur atoms go bye-bye. And we've now gone from here over to here. The next step is to go from moles of the element into grams of the element. That is unique to the problem, okay? That it is important that we're talking about sulfur because we need to use the molar mass of sulfur. In this secondary step, whereas in the first step, we put moles on the top, in the secondary step, I'm going to put the 1 mole on the bottom because I don't want to be in moles anymore. I want to get rid of that and I want to find units of grams of sulfur. What does 1 mole of sulfur weigh? I believe it's 32.02 grams of sulfur. So that will allow the moles of sulfur to cancel. So in the end, we're going to take our large number of atoms, which actually isn't that large, 5.47 to 24. We need to divide it by Avogadro's number. Which would, if you solved, stopped, and then started up again, we have roughly 9.08 moles of sulfur. Then, we're going to multiply that number by the 32.02 grams of sulfur. And 3 sig figs, so 3 sig figs, 291 grams of sulfur. So if you have what sounds like a lot, right? 5.47 times 10 to the 24th sulfur atoms. It seems like so many sulfur atoms. It's only about 291 grams or 0.291 kilograms, which is small. Any questions on that one? On doing a double, stitching them together. This flow chart, again, in my in-person classes, they don't get to use this. You guys get to use your notes. So have this written out like really nice and clean somewhere so that you can just easily kind of flip-flop around. The last thing I want to talk about really, really quick before we go is this step here. So it follows a similar trajectory in that, like, if we want to go from moles of a compound into grams of a compound, we need the molar mass. But instead of molar mass of element, we need molar mass of the compound. Well, how do you calculate the molar mass of a compound? You add all the individual elements up. Okay, so add individual masses up. So the molar mass for something that I can remember, water. Okay, write the formula for water. You need a formula. If you can't write a correct formula, like if I said, hey, what's the molar mass of potassium sulfate? And you couldn't write potassium sulfate, you're going to have a real tough time calculating its molar mass. We should know the formula for water, H2O. So if I want to calculate the molar mass for water, I need to take the molar mass for hydrogen, which is roughly 1.007 or 1.01 is usually what I use. And then you have to multiply it by however many you have. So in water, we have 2 hydrogens, right? So I'm going to multiply that by 2. Then we need to add that to our oxygen. So this first one is hydrogen. The next one is oxygen, which is 16. Yes, I know it's 15.9994. That's close enough to 16. And we're going to just multiply that thing by 1. So the mass coming from hydrogen is 2.02. The mass coming from oxygen is 16. You finally will add those two together, and the total will be 18.02 grams of water for every 1 mole of water. You'll see how there's an extra little step when you're dealing with a compound. You've got to add the molar masses. So I want you to calculate the molar mass for CaCl2 and aluminum sulfate. This one is going to bring back nomenclature. So you got to first write the correct formula. I'll give you guys just about 2-3 minutes to calculate those. All right. So this is calcium chloride. We have calcium, which has a molar mass of 40.00. So it's close to 40. Okay. Like we'll call it 40.01. And there's only one of them. So I'm going to multiply that by 1. Fluorine has a molar mass of 35.45. but I have 2 of them. So I need to multiply it by 2. You multiply by the subscript. Total those out and add them together. All right. And you end up getting 110.98 roughly, and it's grams per mole. The mass of 2 chlorines and throw calcium in there. This one, well, if you don't know what aluminum sulfate's formula is, you're not going to get the correct mass. So you have to be able to write the correct formula. So what is aluminum sulfate? That's aluminum combined with sulfate, SO4, which has a 2- charge. Circle that up, flip flop. I'm going to get Al2 SO4 3. So this is a pretty clunky thing. It's large. So aluminum's mass is 26.98, and there's 2 of them. Sulfur's mass is 32.02, and there are 3 of them. The 3 gets distributed to everything within the parentheses. So we'll multiply that by 3. The oxygen, which is 16, is going to be multiplied by 12. You heard that right. 12. 3 times the 4 gives us a total of 12 oxygens. When we solve for all those, should get something like 341.8, something like that, grams per mole. So that makes it just a little bit more work here. If you happen to be converting between a compound mass and compound moles or vice versa, you've got to actually calculate the molar mass. When you're doing it between an element, you just look it up on the periodic chart. So I'm going to stop there. We are going to attach these things together. So there are going to be arrows here and arrows here. There will be no arrow here. So if you want, you can put like a big red X there. There's no way to go from gram of a compound into gram of an element or vice versa. You have to go the long way. We'll talk about this attachment or these 2 arrows next time. That's to do with the formula subscripts. Otherwise, nice job on the tests. Let me know if you have any questions, general questions, just throw them out there. Personal one-on-one questions, stay around and I'll call you in one at a time. Have a really good weekend. Hopefully I survive and I am in one piece next week for all of you. I'll let you know how it goes. All right. Awesome. Bye, guys. Night, Chrissy. Night, Cynthia. Thanks for best wishes.